Hi everybody, let's talk about the pressure of a mixture of gases, and we do that using something called Dalton's law. So Dalton's law of partial pressure says this. It says that the total pressure of any mixture of gases is equal to the pressure of each individual gas within that mixture. So we're going to apply that law to some problems today, and also we're going to have a special application, which is applying it to when gas is collected over water. So we will do a lab a little bit later on this year, and I have drawn what we'll do in the lab over here. I know it's not a great drawing, but you can follow along. So we'll do a reaction here in the Erlenmeyer flask, right? So this is where the reaction is going to take place, and it's connected by a hose that's over to this green bin that has water filled inside of it, and it has this nice graduated cylinder that is upside down. And you'll notice in the graduated cylinder that the water is all the way up to the very top, right? So the water is filling out the whole way to the top. So as the reaction proceeds and releases gas, the gas goes through the hose all the way down like so, and it starts to bubble in here. There's a little hole in the bottom of the trough that doesn't let water out, but it allows us to have gas go in. And so as the gas enters, gas is really, really light, right? Less dense than air. So the gas bubbles up, it starts bubbling up to the top of this graduated cylinder. And as more and more gases bubble up to the top of that graduated cylinder, all of a sudden the water level is going to decrease, right? Because the water is being forced out of the graduated cylinder by the gases that are coming in. So eventually we might end up with our water level dropping the whole way down here or something like that. And the rest of this space up here is filled with gas that happened from our reaction. And so we can then measure the amount of gas that our reaction gave off based on the water that is displaced. So this is a really common way of collecting gases over water because you can see how much gas you're collecting. If you just tried to bubble gas into an empty graduated cylinder, there'd be no way to see how much gas is in there. So that's all well and good, except that it turns out that water vapor has a pressure. So in addition to the gas that's sitting up here, this red gas that I've drawn in here, there's also a little bit, not much, there's also a little bit of water vapor, so H2O as a gas, that's stuck in here. And so we need to subtract off the vapor pressure of water to get an accurate pressure of our gas. And so that happens with this application of Dalton's law. It's still total pressure is equal to partial pressures, but one of those partial pressures in our case is water vapor. And it turns out that the partial pressure of water vapor is different at different temperatures. So we've given you this nice table that shows you the water vapor pressure at various temperatures. This is a table that you would be given on a test. You would not need to memorize this, but we'll apply that today. So let's dive into a practice problem. We are told that we have some partial pressures of nitrogen, oxygen, and argon making up this gas, and we want to know the total atmospheric pressure. So remember, Dalton's law says that total pressure is equal to the partial pressure of one gas plus the partial pressure of a second gas plus however many gases you have. So we have in this question, we are told that we're dealing with nitrogen, oxygen, and argon. So really, P1 could be the pressure coming from nitrogen, which remember is N2. P2 could be the partial pressure coming from oxygen, which is O2. And P3 could be coming from argon, so that's Ar. And so let's sub in those values. You'll notice that we're given values for each of those. So the total pressure is equal to the sum of the partial pressure of nitrogen, which we are told is 604.5 mmHg, plus partial pressure due to oxygen, which is 162.8 mmHg, plus partial pressure due to argon, which is 0.5 mmHg. So if you add all of that together and you get a sum, you'll notice they all end in the tenths place. So sig fig wise, we want to end in the tenths place. But when you do that math, you will get a total pressure equal to 767.8 mmHg. So this is all well and good, straightforward. You just want to keep track of your sig figs based on the decimal place, and also notice that this only works if all of those pressures are the same unit. So if we were given pressures in different units, we'd need to convert pressure units until we had the same units across the board. All right, let's try number 2. So as soon as we are told that we are collecting oxygen gas or any gas over water, that means that we're going to be using that second formula, which says that the total pressure in a system is equal to the partial pressure of the gas involved, in our case it's oxygen, plus the water we are collecting it over, right? And so we're told that the barometric pressure during this experiment was 731.0 torr. So that's that total pressure, that's the atmospheric pressure. So pressure total is equal to 731.0 torr. It says we're interested in figuring out the partial pressure of oxygen gas, but unfortunately we're not told the partial pressure of water vapor. So what do? Well, we are told that this thing is taking place at 20 degrees Celsius. So 20 degrees Celsius, if we come on up to our table, you'll notice that 20 degrees Celsius has a partial pressure of water vapor of 17.5 torr. So actually we are told the partial pressure of water vapor. It's 17.5 torr at the temperature where our experiment is taking place. So now we just need to rearrange, right? If we want to solve this thing for the partial pressure of oxygen gas, we would simply subtract away water. So if we take the partial pressure of oxygen gas, that's going to be equal to the total pressure minus the pressure of water vapor, right? That's how we'd solve for PO2. We can plug everything in, so the pressure of oxygen is going to be equal to the total, which we said was 731.0 torr, minus water vapor pressure, which we said at this temperature is 17.5 torr. And if you do that math, you'll notice they're both significant to the tens place. The partial pressure of the oxygen gas, which is the gas we're collecting, ends up being 713.5 torr, significant to the tens place. All right, let's try one more. So now we're going to collect hydrogen gas, and we're told we're collecting hydrogen gas over water. So before we do anything else, let's jot down the formula that we're going to use when we collect a gas over water. We know that it is the partial pressure of our gas that we're interested in, which in this case is hydrogen, plus the partial pressure of water, and that's equal to the total. We're told that the partial pressure of that hydrogen gas is 742.5 torr. So pH2 is that 742.5 torr. We are interested in the barometric pressure, so that's the total pressure, that's the atmospheric pressure, that's what we're trying to find. And we also, of course, need the partial pressure of water vapor, which we're not given, but again, we are told it is happening at 20 degrees Celsius. So 20 degrees Celsius, like before, we realized is 17.5 torr. So the partial pressure of water vapor in this case, again, is 17.5 torr. And of course, that's not always the vapor pressure of water. It's only that way in these two problems because they're both happening at 20 degrees Celsius. So let's plug in what we know. We're looking for the total pressure. We know the partial pressure of hydrogen. It is equal to 742.5 torr, plus the vapor pressure of water, which we said was 17.5 torr at this temperature. So if you do that math, they're both significant to the tens place. You will end up with 760.0 torr, or standard pressure. So again, Dalton's law is pretty straightforward. It's just the sum of all of the pressures in a mixture, but it has this cool application where we can do water vapor pressure. So if we have a setup like this in lab, we'll need to subtract away the water vapor pressure to get an accurate reading of our gas that we're collecting.